Sí, 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 que diga si lo voy a mover por ahí para que se le vea en la cámara. Perfecto, muy bien. Okay, then let's start. Good morning to everybody and welcome to the IAA Severo Ochoa Colloquium. Our today's speaker is Professor Ángeles Díaz from the Universidad Autónoma of Madrid, where she is full professor. She has been carrying out research in astrophysics for a number of years already and working in different fields. Their principal research lines are the study of the physical conditions and the chemical abundances of the ionized gas in galaxies, the study of the giant star-galactic H2 regions, the study also of the circumnuclear star-forming regions and the H2 galaxies, the study also of the stellar populations in star-forming galaxies, study of chemical evolution of the spiral and dwarf galaxies, the connection between violent star formation and activity in galactic nuclei, and finally the integral field spectroscopy applied to the case of emission line galaxies. She has participated in more than 25 publicly funded research projects, research grants, and she is co-author of more than 150 papers along the last years. She has been also an active participant in many different international collaborations. Let me mention some of them, like the Lovers of Active Galaxies, the AGN Watch, the project, the Grupo de Estallidos de Formación Estelar, GEFE, the project PINS, that is related to observations with PPAC or Selfish, among others. But besides that, since she has been for many years working in the Universidad Autónoma de Madrid, also she has a lot of experience in teaching activity, where she has developed a career as a university professor for more than 35 years. In fact, during these years, she has supervised more than 20 PhD students and other 22 master students. That's a really big number. And also, as part of the university, she has played different roles as a permanent professor representative, secretary, deputy director, and director of the theoretical physics department, and also research vice dean of the science faculty of the university. But besides that, she has been also very busy with outreach, and in fact, she has been the responsible for many years of the astronomical observatory of the University Autónoma of Madrid. Today, she will be talking about one of the fields where she has been working along her career, that is the study of metals. And the title of the talk is Cosmic Chemical Evolution, Here, There, and Everywhere. Okay, this is without any doubt a very suggestive title. Okay, Ángeles, welcome to the IAA, and the floor is yours.
Well, first, I don't know if you can hear me. No problem. Okay. First of all, thank you very much for the invitation and for having me here and surrounded by good colleagues and friends. And I'm delighted to be here to give you this talk. Yes, this is a suggested title. I didn't know what to put for this kind of talk, which is indeed a colloquium. It's not purely a seminar. And yes, I thought about here, there, and everywhere. And it's going to be mostly here. A bit of there, and a confusion of everything. So, and so let's see how it goes. This. Okay. Well, to start, I just will provide some general background, talking about the importance of metals. And metals for us is everything that is heavier than helium. And I want to stress the importance that metals have in the star formation processes and in stellar evolution, because among other things, they control the cooling of the interstellar gas, and this is what allows the formation of stars to take place. They affect the radiation transport through the opacities involved in the different microscopic processes. They have a lot of importance in the role of dust formation, but also helps to the star formation processes by providing screen to the whole place of star formation, and also in the mass loss from stars, which affects a lot the evolution. So this is a very general background, but metals are formed inside stars. This is the point. So we would expect metal enrichment in the universe to start as soon after the first massive stars form, because they are going to be very short-lived, and these stars will return to the star formation, to the interstellar medium. The chemical elements they synthesize in the interior, and this ejecta at some point will mix, we are not sure of how, but with the surrounding gas, will help again to its cooling and subsequent generation of stars. So this is what we call the cycle of cosmic chemical evolution, and it is depicted here. Well, in the more detailed picture, not all the metals are returned to the interstellar medium in the same way, okay? And not all of them do it at the same time. So oxygen, sulfur, magnesium, alpha elements are synthesized in the nuclei of very massive stars and return to the interstellar medium in a scale of a few million years, very soon. On the other hand, elements which have a secondary origin regarding nucleosynthesis, like carbon, nitrogen, are mainly made in intermediate mass stars, and the time scale to return to the interstellar medium is much longer, about 1 billion years. And iron is produced in closed panel systems, so the production time scale is also large. Also, they do not return to the ISM in the same way. Massive stars through supernova explosions, intermediate mass stars through planetary nebulae, the two examples we have here, and type 1 supernova are the origin of the iron production. So this is a lot of information. It's like a puzzle, and there are two ways of exploiting this information: deriving chemical abundances in situ in galaxies at different redshifts. This has been a process that for many years was very difficult to achieve, and now we see it's becoming in some way easier. We are not very sure. The other approach is to derive chemical abundances at the present epoch, at redshift 0, and use chemical evolution models to predict their abundances at higher redshifts. And then we can confront this with observations. So eventually, these two approaches must converge. Okay. If we can extrapolate the models to earlier times, we can make predictions, and those can be confronted with observations. Again, this has been difficult to do up to now, and it is becoming easier. So we'll start by the local universe. Even that definition is not very clear. What's the local universe? I have chosen this one here, or you can see the distribution of the 2 micron scale survey. And this 003 that I put here could be 5, could be depends on the source. So, well, now I can know. No, don't know what happens. Okay, here. Right. Okay, this is the kind of objects we're going to do now. I mean, spiral galaxies and both irregular galaxies. And in a given galaxy, what we are going to do is to I'm sorry. The analogic. Perfect. What we do actually is to go to these H2 regions, to these entities, and obtain spectra, as you can see here. But this is how we see even a nearby galaxy with a relatively small telescope nowadays. And this is a picture I like a lot because it was taken through the Isaac Newton telescope when it was at the UK, in an observatory that was almost below sea level. And it's Venus. So this is what we have, but in fact, what we have is this. Maybe. Okay. Analogic out. So this is an H2 region of that kind. Here we see it better. And in fact, it is the same. But when you put the object far enough, you will see just something of this kind. This is a giant galactic H2 region. And this is the origin of our knowledge of abundances from nearby objects. So how we do it? Well, as you can see here, I have put a quotation from my propita that said that H2 region emission lines provide the main way of probing the chemical evolution of the universe through cosmic time. Why? Well, because these large H2 regions can be seen at very large distances. So most determinations of metallicity in galaxies out of the local group come from this spectroscopic analysis of the nebular gas that can provide spectra of this kind. Because they have strong emission lines and low continuum, they are easily to spot and easy to observe. Now, how do we do that? Well, fortunately, the emission lines in H2 regions are optically thin, so the flux we measure in the line is related, is proportional to the element abundance. And now, proportional in which way? Well, that constant of proportionality is a function of atomic parameters and the physical condition of the gas. So, for a recombination line such as H beta, we will have that coefficient is the recombination coefficient. For a collisional excited line, we have the coefficient for collisional excitation. This coefficient, recombination coefficient, depends on the electron temperature, but very slowly. And this is very good. It's very little dependent on temperature. We are very happy. Regarding the collisional excitation coefficient, this is not that way because there is an exponential term here. So this is highly dependent on temperature. We don't like that. So we take different ratios of lines, ratios of two recombination lines, for instance, hydrogen and helium, are very favorable. We have these two coefficients, they almost cancel each other. No dependence on temperature, we are very, very happy. Ratios of two collisional lines. Well, not too bad because there are two coefficients with slightly different dependence on temperature and, well, we can handle it. Radius of collisional line to a recombination line, that is most of the rest of the lines, have a strong dependence on temperature. We don't like it at all, but this is what we have. So how do we do? Well, most of the observed emission lines, we say, are collisionally excited. The intensities depend exponentially on the electron temperature. This temperature is not constant through the nebula. So there is the negative gradient that we show here from photoionization models. Usually they show a negative gradient outwards. The different oxygen ions, for instance, are formed in different zones with somewhat different temperatures. It's necessary to adopt an ionization structure that we can see here, also from photoionization models. And how do we do this? Well, first, let's go into the conventional way of deriving abundances, which is using oxygen, because it is the most abundant element after helium. So it is produced in high mass stars. So if we know the abundance of this element, we can be sure it is present-day abundances. Or if we do it in an object of the redshift, it is the abundance at that time. Traditionally, the metallicity of gaseous nebula has been traced by oxygen. So this is what we call metallicity. This is its value for the sun. And then the ionization structure, generally it is assumed as a simple two-zone approximation. So the oxygen twice ionized is in the high excitation inner zone, and the oxygen once ionized is in the low ionization zone, which is the outer. But it is not very clear what we can measure. Sure, we can measure this temperature, and normally we cannot measure this. So this is usually found by fittings to measured values of the O+ oxygen and O2+ oxygen. So it is not very straightforward. It is like a cloud of points, and these are different photoionization models with different electron densities. And this was models this from 1980, but the situation has not changed very much in quite a few years. We still have a cloud of points. So what we do is to choose a line, which is this black line, and represent or derive the temperature of O+ from the temperature of O++. What happens with this for oxygen? Well, if you look at the distribution, this is for nearby H2 regions, and you see that most H2 regions have contributions by O+ to the total oxygen abundance greater than 50%. So if we make an error in finding this temperature, this will translate into large uncertainties, into the average values. And this is increasingly important as the dominance of the O+, the low ionization state of oxygen, is dominant. Okay. What happens if we observed more excited objects like H2 galaxies? Well, again, there are uncertainties in the final average values, but as you can see here, most of the H2 galaxies have low contributions of this ion to the total. So in the low metallicity regime, these assumptions can be made. And this is the reason why there are so many studies of this sort of objects in the low metallicity regime. And very little is known about the high metallicity regime of these H2 galaxies, even in the local universe. Okay. And this has been increasingly going that way, looking for extremely metal poor objects and all this sort of thing. Another issue is that the lines we need to derive temperatures are very weak. And at high excitation like this, which is low metallicity, we can see the line quite well. But for metallicities even past the solar value, we start to see very little, impossible to reach values of this weak temperature. This is actually the nebula. This is, what is it? Here. This one that is on the floor is that small thing here, 45 meters. We have to take into account that the ratio of the nebula to the weak line is about 100. So this is a problem for determining the oxygen abundance of high metallicity regions. So to solve this, we introduced empirical calculations using strong lines that we can measure and trying to relate them to the abundance of oxygen. This is a very used parameter that was introduced by Padilla et al. In 1979. Okay. And this is the explanation of why things go this way. It's just that as the oxygen abundance increases substantially, because the nebula is cooling through the emission of these oxygen lines, then the temperature goes lower. And in this region in which the oxygen abundance is very low, the cooling is dominated by hydrogen recombination, so everything is linear. But when the metallicity is higher, then this trend reverses. This is theoretical modeling, and it looks very nice, but reality looks a bit worse. This is what we have. And you can see that here there are many objects. These are H2 galaxies, actually, and the bulk of them, almost 80%, are there, where there is a large uncertainty in the determination. Well, through the years, there have been many calibrations. Here I listed only 24, there are many more, and we are getting more and more of these calibrations with different abundance parameters. And this is very used nowadays, calibration, supposed to be one of the best ones, but we can see that at this high excitation end, it's not working properly. And we can extrapolate this almost to solar metallicity. Now, if there are people that have been working on this for, I don't know, 40 years, maybe it's a difficult problem. And it's very difficult to add something, I don't know, new or consistent to that. So, is there a solution for this? Yes. Yes. And it's a simple solution. You just have to think about this product. H mu, more or less, should be K by T, because this is the range in which the emission is going to be centered. It is where the exponential in the temperature that we showed before is going to be 1. Okay. And why? Because these are collisionally excited lines. So these lines are getting, these levels are getting excited by collisions with electrons. When we mean electron temperature, we mean that this is the only component in the H2 region that has a Maxwell distribution. Thermal distribution. Again. So in order to excite the line, you need to have the appropriate temperature to excite the ion. Once it is 10, the level is metastable and will recombine back. Okay, de-excite spontaneously. So this is what we have to see. If we have low temperatures, then H nu is going to be low, and the wavelength is longer. So if we are looking for abundances in regions with low electron temperatures, as it happens in high electricity regions, we have to move to the red. And the contrary would be if we wanted to find abundances in places where the temperature is very high. Instead of doing that, we are doing it for oxygen. And this is for historical reasons, because for many years, the visible blue spectrum is the only one that was accessible. But things have changed a lot in the last decades. So, my proposal is using sulfur as a demonstration. Okay, and now I'm going to show you some advantages of this. Well, first, sulfur is also produced in massive stars. It follows oxygen. So it seems that the S/O ratio remains almost constant at the solar value with a lot of scatter. It's true that sulfur is less abundant than oxygen, almost by an order of magnitude, but in principle can be used as abundant tracer, providing similar information. So the far red lines of sulfur are analogous to those of oxygen. You can see it here. They come to the same levels. Okay, but because the energies involved in the transitions are lower, then their emissivities are less dependent on the electron temperature. Another advantage is that these are taken from Bresolin, one of his contributions to a congress, in which he shows this is the limit of detection of large telescope, about from 8 to 10 meters. And then you can see that this is the line, detection line for the oxygen 3 temperature. This is for nitrogen 2, and this is for sulfur 3. And this is the most favorable one. I mean, you can get down to almost 5,000 Kelvin. With oxygen, you can get about 8,000. So for things which are in this part of our graph, we cannot access, I mean, this line gets too weak. And the best advantage is that you do see the lines. And this is, I mean, this is a high metallicity, H2 regions where you don't see the nebula oxygen line. We just don't see it. It is there someplace inside the noise, but you see very clearly the lines of sulfur. Also, it is very clearly detected. The continuum is very clean. There are not many stellar absorptions around there. And the other advantage is that the ionization structure can be quite simple. This is what we take for oxygen, these two zone approximations. But when talking about sulfur twice ionized, same as argon, we have an intermediate zone. And this intermediate zone, as we can see here, it's covering most of the nebula, both for the conditions in H2 galaxies and the conditions in H2 regions. And that means that it is not so important to have a two-zone ionization structure, and we probably can do it only with one. In fact, this is a very commonly assumption, something very commonly assumed, that we can get the temperature from 2, 3 from this expression. This comes from photoionization models. And we can get this also, the temperature of sulfur 3 as a function of the temperature of O3. This is empirical. And if you take these two things together and assume that both S plus and O plus ions are in the same zone, then you will get to this. In fact, this is this relation, and the other one, the dotted one, is the one-to-one relation. So then we're very close to that aspect. So in most conditions in moderate to high metallicity, we can make this assumption that both temperatures are the same. They are both in this intermediate region in the nebula. And this has been confirmed in late years. This is the group of the Chaos project that have lots of data taken with a large binocular telescope. And then you can see that the temperature of sulfur 3 is very closely related to that of nitrogen 2, which is supposed to be in the same zone that the oxygen 2 ion. Okay. So this is 2016, 2020, 2021, we still have the same result. So if we make the assumption that low ionization ions are formed in the same zone, N2, S2, and then we can make safely the assumption we did before. Well, once with that ionization structure, that assumption, we calculate the total abundance distribution, so we can get this, and we will see that both in H2 regions and in H2 galaxies, S2 plus dominates the sulfur abundance. But in H2 galaxies, we have a small population of galaxies, or smaller, that need to account for the presence of S3 plus. And the first sulfur 4 line is in the infrared. So we need to provide here ionization correlation factors that we do by finding that the ICF correlates well with this eta prime parameter, that it is a good indicator of the ionization temperature. This has sense because we need high energy photons in order to produce S3 plus. So doing this, we can get the ionization correction factor, and we have contrasted this with observations that have been obtained from the infrared. And well, for the few objects we have, it's going quite well. And what about the empirical calibration? Well, the effect of sulfur ions as pollinators is evident. I mean, this is the correlation shown between the total abundance of sulfur and the temperature. That means that effectively this is what is cooling the nebula down here. And this is interesting because this is the base of the empirical calibration. We forget about that. But in the paper by Padel et al. That defines this R2-3 parameter, it is this relation what he's showing. He's defining an average lecture temperature that is related with the parameter. And this is essentially this, if I put it here, like this, because it is specular, but this is what he found. And this is the base of the empirical calibration structure. Any calibration should reflect this fact. And this is the calibration we find for H2 regions in disks of galaxies. and H2 galaxies, which has the good point of being linear. I mean, it's not twofold as it is the case for oxygen. So we have introduced this S23 parameter. The lines of both sulfur and S3 can be measured relative to H alpha, thus minimizing the effect of reddening. There's no question about that. And the lower temperature dependence renders the lines observable up to oversolar abundances. And due to the longer wavelengths of the lines involved, this relevance of the cooling agent starts at lower temperatures. Eventually, this is going to, and we think that this is already starting to bend in the same way as oxygen does, but at lower temperatures, higher metallicities. Well, this just to show that there is no dependence on the ionization parameter, and there is a dependence on the temperature of the ionizing radiation. This is just to show you that photoionization models, as you see here, start this bending. The contours are our data, and these are the models. So, in principle, models are in agreement with data. Now, is our knowledge of the metallicity distribution complete? Probably not. For H2 region abundances, the calibration I showed before, Marino et al., is the preferred calibration, and probably is missing high excitation, low metallicity objects. Using the S23 parameter, we can cover from the lowest metallicity objects to those up to 3 times solar. Now, if you look at Khalifa survey, and we look at the central metallicities, looking at the metallicity gradient, we can see that we get to solar is 869, well, a bit more than solar. And this is for 4,500 H2 regions in 200 galaxies. If going from Khalifa to Muse, we get a bit lower than that, but still we are on the range. But they have been identified this now called central abundance drops. That when you get to the center of the galaxy, in some galaxies, there is this drop in abundance. And interestingly enough, central drops, this is with and this is without, are preferentially found in the most massive galaxies. So this is something to take into account, that maybe there is something that is hampering us from reaching high metallicities using parameters for oxygen. And it's quite reasonable because in this R23 calibration, there is no A3. It's only on 2. So it doesn't mean that there is no ionized oxygen twice, and there is, but the emission is going through the infrared lines. The oxygen is there, but the temperature is too low, and then most of the energy is coming through the infrared lines of oxygen 3. So the mass metallicity relation is probably still incomplete, since metallicities traced by oxygen cannot reach over solar abundances. So this is the paper by Cully and Ellison of some years ago that had a lot of impact, because it shows that depending on the calibration you use, you get a different mass metallicity relation. And this is the last one that I have found for nearby objects, gets at all. And well, it gets to here, less than solar, because this group is doing abundances with deriving temperatures from the direct energy. So you don't get farther than that. On the other hand, for star forming H2 galaxies, as I told you before, most of the work is devoted to extremely low metallicity objects. And also, when you require the presence of this line, this introduces a lot of biases. Okay, so it has been shown that the non-detection of the line is a real metallicity effect for at least some fraction of cases, but also objects without the auroral line are about 0.4 dex more metal rich than objects with it. And it has to be with the stellar population of the objects. If the H2 galaxy is like the mass, all the stellar population, ball, then the continuum is very high, the low is very weak, the line, and then it's difficult to see the line. And as I told you before, more than 50% of all galaxies fall beneath of the most used calibration. This is what I mean here, that in order to have the complete distribution of galaxies, abundances for these kind of objects, you have to consider both the ones that show the line and the ones that do not show the lines. And we have here population of metal-rich regions, okay, which have high excitation, high metallicity, that we are missing from the sun. Well, we have recently done an analysis of SDSS, star-forming galaxies, and these are the different samples. Sample 3 has objects with both the electron temperature of O3 and S3, sample 2 only S3, and sample 1 there is no T measure, and they make a large contribution of the high metallicity that are missing from the samples. Well, regarding the mass metallicity relation for these star-forming regions, I couldn't get a clear conclusion. So we are still working on that. The errors are large, and the empirical calibration used by many people are the one by Tremonti et al. That overestimates metallicities. Now, this was here, now we go there. Where is there? This is difficult to say also. There has changed a lot in the last 5 years. So when we refer to moderate or intermediate redshift, we were talking about 0.8, 0.9, maybe 1. Now this is definitely at home, because intermediate redshift is 3, 4, 5. High redshift is 10, 9. Well, this has to do with the evolution of the space telescope, James Webb. And also for a flavor of what objects you can find at different redshifts, this is how they look. We find chains, we have clumps, we have morphologies which are not defined, mergers, all this kind of fauna. They are not the same well-defined objects that we were looking at when we refer to the nearby universe. Okay. I have taken here a redshift between 0.03 and about 1.52, depending on the study. And up to 2005, there were very few students of field, no field galaxies. And one of the first derivations of abundances by direct methods were made by Hoyos et al. In 2005. And he found that in the luminosity metallicity plot, they were below other objects that instead of using direct derivations of the electron temperature were using empirical calibrations. Okay. And of course, it could be a selection effect, because in order to see the line, as we said before, that is a large, but maybe these objects are not purely representative, and maybe are in the range of what we call now extremely metal poor, and some time ago were luminous blue compact galaxies. Okay. Is this kind of object, and this is the spectrum that he was working with. This one was continued later in Perez et al. Finding the same thing, but in this case, the objects are representative. They are not blue luminous compact galaxies, but they are normal H2 regions with normal equivalent widths of O3 and H alpha. So we still find this, which is below the relations found by Tremonti, for instance, and Said. These come from empirical calibrations, and these come from directly derived temperatures. Still some more work. There are by Lee et al. This we can say is the first systematic study of the evolution of the mass metallicity relation up to redshift about 1, using only the T method for abundance determinations. And what he provides is the change in metallicity with look-back time. But as you see, with a lot of scatter also. Another one is the work by Lee et al. That studied the ionization gas metallicity of the strong emission line. These are strong emitters, let's say. And they find this distribution, whatever it is, that is not being reproduced by, maybe this is the best one in this. So a lot of work to be done yet there. And finally, Yang et al., just a few years ago, produced a direct electron temperature metallicity calibration of this parameter R23. We are still engaged with R23 for galaxies in this range of redshift. And what he finds is that there is a dependence on the excitation. Okay, I mean the ratio of O3 to O2 lines. And this is surprising because when you do this exercise with models and so on, where you find the dependence with this parameter is here, and this is matched by the difference in the temperature of the ionizing stars. That as metallicity gets higher, the stars have lower temperatures. So this will have to be revised. And they say that since Greenpeace or blueberries, or I don't know, well, are best nearby analogs of high redshift Lyman alpha emitting galaxies, this new calibration may offer a good way to estimate the metallicities of this kind of objects. So this we can still and go to the part of confusion. So this is how to trace metals far, far away. And I call it the James Webb Steel revolution. What happens that when you enter there and you go to your preferred database, which is ABS, and you look for objects with James Webb Space Telescope in the title, you find more than 1,000 papers referring and a double if you take everything into account in the last 2 years. Thus, refereed articles. It's difficult to digest. Well, if you put abundance in the abstract, you get reduced list of papers. Still, it's difficult. So what I've done is to look for the things that I thought it was most interesting. One is this direct electron temperature based metallicities for redshifts between 2 and 9. And these are empirical calibrations applicable from reionization to cosmic noon. It's a nice title. Okay. This is the paper by Sanders et al. And here you can see that the star formation rate is larger than for other objects. We leave it there. And these are the calibrations they propose. And some of them are really very loose, not many objects. But, well, this is the way we will have to proceed from now onwards, because a lot of things are going to come. The other paper that I liked is this one. It has nothing to do with it, because it is a very detailed study of this sunburst arc, which is very well known. I didn't put an image. Well, and this is a strongly lensed object, so they have made a very detailed study. They measure almost all temperatures or electron temperatures of many ions. You can see the relations here. And the spectra looks very nice. So I like it especially because the point they have here correspond to the 1-to-1 relation between the electron temperatures of the sulfur plus and sulfur 2+. So it seems that at that redshift things are not so different, at least. And it's a good relation. Now, this is just a final remark with all of them. Nowadays, instrumentation limits for the use of the sulfur methodology have been greatly overcome. I mean, from the ground, we have spectrographs, many. I have just chosen this X-shooter spectrograph, for instance, and this can accommodate in the visible and in the infrared bands the emission lines needed to apply this methodology, minimizing scarce of fashion problems for more than 1 million SD galaxies in different redshift ranges, from 0.17 to 1.5, and presumably a good portion of these should present emission lines associated with present star formation. It's just a matter of finding them and doing the work. From space, observations made with near-spec on board of James Webb Space Telescope, whose spectroscopic range starts at 6,000, would be able to provide data for objects with redshifts between 0 and 4.24. And this is because the sulfur methodology uses only the red part of the spectrum. It starts at 6,000 space. It doesn't need the visible blue part of the spectrum. Okay. Thank you. Thank you.
Thank you, Ángeles. So we now start to the question session for the talk. And your time, okay? Questions for Ángeles?
Everything was so good.
Was very interesting. I think, yeah, Ricardo.
I would like to know your views about a recent JWST results showing that we have some mature galaxies, presumably enriched galaxies at high, unusually high ratios. How we can use all these, in particular sulfur, to, if you think that this could be useful to investigate the enrichment of this.
The numbers I have put here are the ones I have worked out. And in fact, you don't get the ranges of 8 or but the point is that the ones that I have seen, there are several publications of this kind of effects, is that they are low metallicity objects, but not so low. I mean, they are very low metallicity objects, but also there are some objects in which the oxygen abundance is found to be 8.4, 8.3. Well, that's moderate to high. I mean, at that point, the assumption that the O plus is not contributing is not that good. But if you include that, the metallicity will be high. Errors are large also. And if you look at the errors in temperatures, in some cases are 50%. Then not be real determinations of temperature. Maybe we should look for better calibrations, but up to 3 I think is not the right time to use. Some time ago, with Enrique Pérez Montero, who's not here, we proposed to use the neon lines for those objects at higher redshifts, with using another parameter and using H delta line instead of theta, but it has not that well tested. So maybe we should, as we said before, if we are looking for high electron temperature and low metallicities, go to the group. So, I mean, it depends on K by T, and this is really, and this is theoretical, and it's, you cannot avoid it. If you look for metallicities large, and go to the right. If you look for the contrary, go to the group. Oxygen is in the middle. It's like the sun. It's in the middle of everything.
More questions?
And I really like the proposal of just changing and move to sulfur because of all the advantages. But you also, sorry, you also mentioned at some point that the sulfur to oxygen ratio remains mostly constant.
Yeah.
But not always.
No.
There are some discrepancies and
Yes.
a lot of scatter.
I think it's not. I mean, I got this result back in 1991 for the H2 reuse in 51, that the SO ratio decreased with the increase in abundance. But I'm talking about tracing abundance in myself. So it's not that important, the relative SO ratio. That is strictly related to nucleosynthesis. It's very good to know because it can give a lot of information about the INF. Because sulfur is produced in massive stars in a small mass range, smaller than the ones that produce oxygen. It's a good point to study, but it's not going to change the tracing of abundance. Now, once you decide to trace abundance by sulfur, you have to stay with sulfur. And then you can make your, this is large metallicity, low metallicity, this is sulfur, using sulfur. In the moment you start to blend oxygen and sulfur, things happen because oxygen is depleted in dust and sulfur is not. So if you make, I don't have it here, but I can show it to you later. If you make the S over O ratio versus the oxygen over H ratio, you get a different answer than if you use in the x-axis the S over H ratio. Because in the first case, oxygen in the y-axis and the x-axis is deleted, and this depletion is probably related with metallicity. And if you use the sulfur in the x-axis, then there is no reduction in that. So you have to take these things into account when relating abundances. It's the same as the N over O, but they give a lot of information in the interstellar physicists and the iron.
Another question? I have some comments anyway. Question. Because I want to exist in the question by part of the question of Ricardo for the high ratio. But well, it's very nice to see that you know, eta, S23, the S over O, all this kind of what I did my PhD and later is now, I mean, is still there. But the main point here would be whether we can actually state or, I mean, derive an accurate or credible abundance for galaxies about, you know, more than 9 in ratio of 10. Is it possible, or do you think it's not possible?
The first thing that is lacking here, to my from my point of view, is to find out if the mode of star formation is the same at X0 or at X8. Because that makes a lot of difference. I mean, all these pumps and chains we have, I don't know that Elmer started to talk about some time ago. This is not the typical star forming mode that we see in the local universe. It's totally different. And so the physical conditions,
those two regions will be different.
yeah, because the physical conditions will be different. In fact, in some of these recent works, electron densities are high. Why? And we will have to go to map not only the ionization structure, but the density structure. Because it is possible that all 3 lines are being formed in denser regions, and the other lower ionization ions are formed in lower density regions. That makes a lot of difference. In the local universe, we find that everything is well below the critical density, so we don't care. Because it is the same to use 50 and 100. But it's not the same to use 5,000.
Yeah.
So we have to do that
more carefully. So study I think that what happened, you maintain this point, that using the James Webb Space Telescope or using the infrared for here, H region, not just the very far away ones. So using infrared lines to study the ionization structure in the infrared, it will be very interesting. More things, more questions,
Next one online.
Go ahead.
Yeah, Almudena Prieto.
Almudena Prieto.
Open your mic.
From the east. Hola.
Sí. Hola, hello, hola. Very nice, Ángeles, very nice, very clear. I like it a lot. I have a question regarding the destination of these lines, either you use sulfur or oxygen. when you are looking at the low redshift and you look at H2 region, it's perfectly defined what are you looking at. We know the citation well, there are stars there in this H2 region. When we get to galaxies, things becomes more complicated because we sum up many sources in the galaxy. So how much, in your opinion, how much is this potential contamination to the excitation of these lines by other mechanisms that are not due to as you say, photonization from the lines? So we might have other mechanisms.
Yes. I understand what you're saying.
Yeah.
And it's true, and this is becoming more and more important since the integral field spectroscopy came about, because now we have a lot of spatial resolution, even at times too much. Everything I've said here regards, let's say, an average object, as I said at the beginning, is an H2 region which is very complex, that we put very far away, and we see it like a unstructured object, no resolution. So then everything there is going to be dominated by the highest temperature source. If it is a star cluster, it's going to be dominated by the more massive and hotter stars. And the rest contribute, but not that much. But obviously this is an average. So, for instance, when you get to higher resolutions, you might need to take into account shocks, because in this region, for instance, that I showed with this ABC604, you see filaments. And probably those filaments, same as happens in Fecha, when you get to high resolution, shocks are there. You can see them as regions. And obviously those regions have a high surface brightness. So when you average everything, you're going to pick them. So yes. I said detailed picture, and this is the super detailed picture. And yes, but this is again some work that you have to do very, very carefully and in a lot of detail. But of course, you're right.
But it might cause the dispersion that you see in this metallicity relation as we go to higher and higher redshift.
Maybe. This is what I mean when I say the modes of star formation may be different. Because, of course, if you see a change of clumps, which are compact, so what are you really measuring?
Yeah, exactly.
One of them, or all of them, or you observe all of them? In some cases, there are several spectra for each object. And the thing they are doing is to average them all.
Yeah.
Well, it's okay for a 0-point version. But we have to go to 1.0, 2.0, and so on. Thousands of papers. I should think, I really think that there are a lot of data from HSP now available to everyone. And this is a very good news. Data are there, you can retrieve them, you can analyze them, reanalyze them, whatever you do. And the bad news is that it is so much to digest that I won't have time because I'm retiring soon.
But if I might say, I think there is a very good perspective now for some with the GMWST in these gravitational lens systems that are discovered at very high redshift, where they claim they might be clusters. These are ideal targets if a spectral can be taken, of course. But it might be others.
There are objects which are behind the known cluster, and they are amplified, and there are observations of those objects. But it's my feeling that now with data from James Webb, there is a lot of pressure to publish.
Yeah.
And we have to digest things a bit more slowly.
Mhm. Okay, thank you.
Okay, something more? Well, I had just a final question because I see Raúl here and we were commenting the other day. So that's so, I mean, one thing is you mentioned the paper by Keely, you know, this. And Ellison 208, which was a sort of scandal to say this is, you know, it's a mess. But this paper referred to, I mean, the origin of the paper was say that, you know, you don't use that because this is a mess, something like that, and then recalibrate all of them and so on. So I used to say, now there's other, you know, photos that, yeah, that was in 208. So now we are not in 208 in relation to the calibration. So I think we are much better than in those days. What do you think? So you don't have to use now this calibration out of date.
Concern with, I mean, this are the relations because when you have like 5 orders of magnitude in the x-axis and only 1 or maybe 2 in the other one,